Hello everyone, today we are going to analyze this beam using strain energy method. In this beam, we have uniformly distributed load for the full span. We have to derive the expressions for the fixed end moment at A and for the vertical reactions, and then we have to draw the shear force and bending moment diagrams. Now let us find the degree of static indeterminacy. In this beam, the number of unknown reactions and moments are 3. They are MA, RA and RB. The available equilibrium equations are 2. The degree of static indeterminacy is equal to 3 minus 2. We will get 1. Let us keep RB as redundant. To find RB, we are going to use strain energy formula. U is equal to 1 upon 2 EI into integration of m square dx. To find the moment, we have to make sections in this beam. In this beam, we have uniformly distributed load for the full span, so only one section is enough. You can see that I have made a section at a distance of x from the point B. In this formula, the limits for the integration will be 0 to L. Now let us find the moment about the section. We are going to find the moments from the point B. In this case, we are moving towards left hand side. Clockwise will be negative and anti-clockwise will be positive. RB is acting in the anti-clockwise direction so that it will be positive and the distance is x. The uniformly distributed load is acting in the clockwise direction so that it will be negative. For the uniformly distributed load, we have to multiply with the distance and distance by 2. Here the distance is x, so x into x by 2. X into x, we will get x square. Now let us use Castigliano's second theorem. In the point B, there is a vertical support, so the deflection in the point B will be 0. In this case, when we partially differentiate the strain energy U with respect to RB, we will get 0. Let us partially differentiate U with respect to RB. When we differentiate M square, we will get 2M. Inside M, we have RB. So we have to again partially differentiate M with respect to RB. Let us eliminate 2. Let us apply the value of M. Let us partially differentiate M with respect to RB. First, let us take this term. For RB, it will be 1. In this term, there is no RB, so the differentiation is 0. 1 into x, we will get x. Let us multiply x with this term. We will get this. We can take 1 upon EI on the other side. 0 upon 1 upon EI, we will get 0. Using this formula, we can do the integration. When we integrate x square, it will be x cube upon 3. When we integrate x cube, it will be x power 4 upon 4. Then let us apply the limits. No need to apply the lower limit 0, only apply the upper limit L. We can take this term on the other side, so it will become positive. Then let us take L cube upon 3 on the other side, it will come inversely. We can eliminate L cube, here we will have L. Finally, for RB, we have made an expression 3WL upon 8. Now let us apply the rule sigma V is equal to 0 and find RA. RA and RB are acting upwards, so both of them are positive. The UDL is acting downwards, so it will be negative. For the UDL, we have to multiply with the distance. Here the distance is L. W into L, we will get WL. For these two terms, we can take LCM. Let us keep 8 as LCM. 8 into WL, we will get 8WL. 3WL minus 8WL, we will get minus 5WL. We can take minus 5WL upon 8 on the other side. So it will come as positive. So for RA, we have got 5WL upon 8. Now let us apply the rule sigma m is equal to 0 and to find MA. I am going to take movement about A from the point B. In this case, I am moving towards left hand side. Clockwise will be negative and anti-clockwise will be positive. RB is acting in the anti-clockwise direction so that it will be positive and the distance is L. UDL is acting in the clockwise direction so that it will be negative. When the UDL comes, we have to multiply with the distance and the distance by 2. Here the distance is L, so L into L by 2. Let us assume that MA is acting in the anti-clockwise direction so that it will be positive. L into L, we will get L square. For these two terms, we can take LCM. Let us keep 8 as LCM. For that, we have to multiply this term with 4 in the numerator and denominator. 3WL square minus 4WL square, we will get minus WL square. Then we can take this term on the other side, so it will come as positive. Finally, for MA, we have got WL square upon 8. Now we are going to draw the shear force diagram. To find the shear force in the point A, we can use right hand side rule. Upwards will be positive and downwards will be negative. Using that, for shear force at just right of A, we will get 5WL upon 8. To find the shear force in the point B, we can use the left hand side rule. Upwards will be negative and downwards will be positive. Using the rule for shear force at just left of B, we will get minus 3WL upon 8. Here you can see the shear force diagram. In this point, the shear force becomes 0. So in this point, there will be maximum positive bending moment. In that point, let us make a section and let us keep the distance as x. We know that in this section, the shear force is 0. Let us use left hand side rule. Upwards will be negative and downwards will be positive. This load is acting upwards, so it is negative. The UDL is acting downwards, so it will be positive. When the UDL comes, we have to multiply with the distance. The distance is x, so W into x. We can take this term on the other side, so it will come as positive. Then we can eliminate W. Finally, for x, we are getting 3L upon 8. Now, let us find the maximum positive bending moment. This load is acting in the anti-clockwise direction, so that it will be positive and the distance is 3L upon 8. The UDL is acting in the clockwise direction, so that it will be negative. When the UDL comes, we have to multiply with the distance and distance by 2. L into L, we will get L square. 8 into 8, we will get 64. Here also L into L, we will get L square. 8 into 2 into 8, we will get 128. For these two terms, we can take LCM. Let us take 128 as LCM. For that, we have to multiply this term with 2 in the numerator and denominator. 18WL square minus 9WL square, we will get 9WL square. So the maximum positive bending moment is 9WL square upon 128 and it occurs at the distance of 3L upon 8 from the point B. Now let us find the bending moment at A. Here we can use right hand side rule. Clockwise will be positive and anti-clockwise will be negative. MA is acting in the anti-clockwise direction so that it will be negative. Here you can see the bending moment diagram. In this point, the bending moment becomes 0. This point is called the point of contraflexure. Let us make a section in this point at a distance of x from the point B. Let us find the moment in this section. This reaction is acting in the anti-clockwise direction so that it will be positive and the distance is x. The uniformly distributed load is acting in the clockwise direction, so that it will be negative, and the distance is x, so x into x by 2. We can eliminate x, also w. 4 2s are 8. So for x, we have got 3l upon 4. We have got this distance from the point B. Suppose we have to find the location of point of contraflexure from the point A. We have to subtract 3l by 4 by L. When we do that, we will get L upon 4. Now we are going to end this session. Thank you for watching this video.